Looks like it's time. Welcome back, folks, and happy Thursday. We're nearly done with the third week, so the course is kind of on its way so far. And one thing I want to mention with how the course progresses, it's going to be essentially everything you're seeing on these blocks in Canvas on a week-by-week basis. The only exception will be on the weeks that we have an exam week, but as we get to an exam week, they'll be presented in this pretty much the same exact way as well. So you'll always pretty much know what's going on, what's upcoming for due dates and those kinds of things based off the information here. Also, I have the due dates that are from WebAssign as well. They should be posted under assignments, which means you have a calendar date on each one of the sections in WebAssign. I also posted your grade from WebAssign. I'm going to start posting this on a regular basis as we start crossing due dates. The first section that came due, section 2.1, I believe that was on the 27th. And so now that gave me an opportunity to post the grade there. And after I grade your quiz one, should have this graded on Friday in pretty short order. I'll get it uploaded onto grades here as well. That's a good idea to just get in a regular habit of checking those grades, making sure everything looks accurate, not just in this class, but all of your classes. If anything's missing, don't hesitate to just reach out to me and email at any point. And one thing I also want to mention, for the way I'm posting the WebAssign grades, all I'm really doing is going directly into the WebAssign system itself and taking your average score amongst all assignments that have gone past the due date. And so I'm just uploading that particular score as one overall grade. Well, there's other things to talk about in announcements, but any questions so far? Okay, I'll be giving everyone direct feedback on your quiz one. If you turn in a hard copy, say physically in the classroom, because we're coming into an exam week, what I'll be doing is scanning that and emailing it back to your ISU email address. For everyone else, you can see under Canvas, under the assignment, I'll be uploading your feedback and any comments on your graded quiz number one directly through that system. And for quiz number two, this one's going to be based off the continuity section 2.3. And notice that is the last section on the material coverage for exam one. So we talked about this Tuesday, but it's a good idea to reiterate. Probably a good order of operations for studying for the exam is get caught up on all quizzes. Even if you forgot quiz one is due today, if you get this done on, say, Friday, Saturday, or Sunday, I'll be able to grade that. I don't have a late policy, so I'll grade it for full credit and send you back the feedback to help you out on the exam. And I like to grade my quizzes on the due date since I'm just more efficient if I'm grading them all as one big set. But quiz two is special. It's based on section 2.3. And so if you're studying for exam one, getting quiz two done is probably a great next step after quiz one. If you do this quiz early and turn it into me, say sometime on Sunday at the latest, I'll make every effort to grade it and send it back to you so you can get that additional feedback for the upcoming exam one. Well, let me show you what quiz two looks like now that we're talking about it. So same kind of format for posting the quizzes. It's just a link to a PDF. We'll do that all the way down on all the quizzes. And it's a hand-drawn kind of problem, sort of like what you saw in class. You're going to find the numbers where its graph is discontinuous, and then indicate the type of discontinuity, whether you're looking at a jump discontinuity, a removable discontinuity, or an infinite discontinuity. Dashed line is meant to be a vertical asymptote. And then say whether the graph is continuous from the left, right, or neither at each one of those discontinuities. You'll probably feel like you've got a bit of a deja vu. We did this also in the lecture notes. There's problems along these lines in the homework. That means as a pretty good hint on the upcoming exam, if you solve quiz two, you should expect a pretty similar kind of problem on the upcoming exam. And that's kind of my goal with all of the quizzes. They're meant to be like hints of stuff you should expect on upcoming exams. The way they will be formatted, the way I'll ask the questions is pretty much what we're doing on each of these quizzes. So that's a lot of announcements so far. Any questions at the moment? Okay, so order of operations for studying for exam one would be get through the quizzes. It's just quiz one and quiz two so far in this course. After that, get caught up on the sections on WebAssign. There's 3 sections on the table. 2.1 is past due already, but if you went inside WebAssign, either click directly on this link or this one here if you're just getting started. You can always go back to those past due assignments. L Wild says, when do you expect to have quiz one graded? I expect that one should be graded sometime on Friday. It's going to be one of the very first things I do. So if I was to give a timeline, probably sometime before 1 p.m. Usually I start working on answering emails, then moving into grading the quizzes and such right around 8:30 a.m. So probably sooner than 1 p.m., but on the earlier side. Other questions at the moment? Okay. So again, if you're, say, getting caught up on these sections on WebAssign, but any section happens to go past due, here's what it looks like in the WebAssign system. There's one past due assignment, it says. There's two right here. I would say ignore 3.1 and just really laser focus on the exam one material studying until you feel like you just want to work ahead. I think that would be okay to leave it off for the moment. Your past due assignments are in this link right here. So if you click on this, it's kind of annoying in the, oh, there's two of them, it turns out. This one was due at when class started, 4:30, and we just crossed that mark. It's kind of annoying how WebAssign does the extensions because my goal is to not really have a late policy. The due dates are for the sake of pacing. If you're getting the work done by the due date, you're considered fully caught up with this course. But if you went back to this material for the purpose of studying exam one, that's another great thing for the sake of studying. So I wouldn't want to like lock you out of this. But you have to do this weird little rigmarole to get back into section 2.1. You click on request extension, and manual extensions are not active for this assignment, is what it'll say next. Jacob says for the Canvas post for each WebAssign section, does it work just to put done in the submission? Actually, you wouldn't have to say anything at all in the submission. It was more for the sake of just having a date on the calendar. But yeah, if you put just something like done, that would be just fine for the submission on that one. I think that'd be a good idea if you want to clear off the calendar, which is another thing that could be kind of a weird thing going on in Canvas. So yeah, that would be just fine. And now that I'm thinking about that, I might be able to set that up so that it clears off the calendar once it's past the due date. So you don't necessarily have to write done on each every one of them. That could be kind of annoying. So I'll see if I can tweak that out a little bit better. I'm definitely still learning how Canvas works. But for as far as requesting an extension, once again, just click on this link. It says something is broken, but what you're supposed to do is click on automatic. I'll have it so that you can just automatically extend this and not have to hassle about doing anything like sending me an email to approve it. Click on automatic. 0% off is just my way of saying there's no penalty on this. So if you're behind on 2.1, you can still get full credit on this. It says 7 days. So every time you go for an automatic extension, it's a 1 week extension. Accept automatic extension and request submitted. New due dates posted. And if you missed that due date, maybe there's just one last question that you didn't get to and you want to go back into it, just repeat the whole entire process, re-extend it again, and you can go back into work on it. Let's see, click current assignments. Where to go? I guess I have to be on past assignments still. Maybe all assignments. Okay, maybe all assignments is the more sensible one. Click on section 2.1. It should now be unlocked. Let's double check that. And hey, it looks like it's all set. You can now start working on this, improving your grade. Again, there's no penalty here. It's definitely not something you want to take too much advantage of, but sometimes weeks kind of get away from us. If you're getting behind for any reason, you can always go back to those sections to reclaim the credit. So it's a lot of clicking on just to get back into an assignment. So just to kind of refresh on that, to go back to, oh, it appeared on this list again. So if I wanted to work in section 2.2, I'd click on past assignments. I just click on it, see what it says. Gives me big red bar here saying due date has passed. It looks like we're just out of luck on this and I got 0% on it. But if you click back, go to the past due assignments again, the navigation's kind of clunky. Then just for short, request extension, hit automatic. So click on the here until something works and you get a menu. that says automatic extension down below. And now you can work on this section. So click that away, click on 2.2 again, and it's going to appear on your overall list. Now there's no red bar saying you can't do anything here. You can start working on these problems. And if you go back to these sections just for, say, the sake of practicing it for the sake of the exam, maybe you've gotten fully caught up on section 2.2, but you want to look at these problems again, sometimes you can click on practice another, but it does depend on the problem. Sometimes it doesn't always give us a different problem. Did this one change? Let's see, practice another. Looks like the graph doesn't really change, but maybe the stuff down below changes. No, it looks like this problem doesn't give you another fresh view or a fresh problem to look into. I think the graphs are pretty static in that sense that they don't give you a new graph. That's kind of unfortunate. But let's take a look into problem 4. If you want to practice a different version of this one, even if you've already solved this problem, you've already gotten your credit, you can come back in, click practice another. And I believe that did give us a different function, but let me look at it more carefully. Yeah, they change every time I click the button. There's not a lot of versions on that, but it gives us something, a different version to work on. Here's the practice another version. And just another standard offer. If you're getting caught up on the homework on WebAssign, say you're working on Friday, Saturday, or even Sunday, don't hesitate to make liberal use of this button right here. Every day I get up, even on the weekend, I'm going to be looking into my email, especially when we have an upcoming exam, and I'll answer all the ask your teacher questions that you pose to me to help you get prepared. Well, that was a quick rundown of extending sections back in WebAssign. Let me get back to where we were. So the topic we were talking about is for an order of operations on practicing exam 1, just to refresh, get caught up on the quizzes, get caught up on those sections on WebAssign, even the ones that are past due, you can request an extension and work on them. Then after doing all those work, if you want additional problems, additional practice, you can see either of these versions. Version 1 is new problems out of the textbook. So you just go to the eText in WebAssign to see those problems at the end of the sections. And this is the lecture notes now blanked out to make them look like actual real exam questions at that point. Well, that was about 13 minutes of announcements. Any questions at all, folks, so far? Okay, other piece of advice as it comes to exams. The first exam is probably the one that makes you the most nervous because you're wondering, how am I going to write these questions? How many questions are you expecting? What's the level of difficulty? As far as the level of difficulty, I'm a big fan of parallelism. It's going to be about the same level that you're seeing in the homework sections, the quizzes, and the lecture notes that we've been going through on a day-by-day basis. I'm going to write very similar kinds of questions. If we did a lot of graphing questions like in section 2.1 and 2.2, you just should expect graphing questions again in the actual exam. We did some graphing on the continuity section, so you should see graphing questions there as well, for example. And for how many questions are going to be on there, I usually am going to go for an exam that doesn't force you to write for 75 minutes, but has about a 60-minute in length for carefully considering every problem, and with the last 15 minutes to just double check your work. So the average student should get this completed well before the 75-minute mark. Still, kind of pace yourself. I think I'm asking about 6 questions on this one. I don't know the exact number, so about. I'm not going for like 12 questions, for example. So if you pace this out for around 10 questions or 10 minutes per question, then you'll do great on this exam. So we don't have a lot of time in the schedule for review questions or review days ahead of the exams. And that's another reason I try to make the exams pretty in line for what we actually did in class. It'll be very almost deja vu kind of problems coming back. But at the start of every single class, I'll still call for questions no matter what the day is. So I'll turn it back over to the class. Any questions or comments at the moment, folks, to start us out today? Okay, well, again, a big hint on the exam is if you see quiz problems, think of them as like real exam questions. Try to solve them as if it was a real exam question. In particular, we mentioned a lot. We did this problem in the continuity section. It's a tricky problem. So practice this one while taking a look to how we did in the continuity section, and you'll get some really good practice on a real exam question. And another really tricky exam question was this one. I almost skipped over it, so sorry about that. That's why it's in red. A really strong reminder for me to not skip this question. We mentioned at one point in this course that there's three major topics in a calculus course. It's continuity, differentiability is the next section, and integration is going to be chapter 5 is when we'll start that. And so sometimes there's questions that relate to those three big topics, but the theme is all three of those topics, continuity, differentiability, integrability, they're all defined through a limit. So that's what the example 3 question is all about. You should expect this kind of question on the real exam 1 and possibly the final exam as well, since it's one of those big concept tie-in kind of questions. And here's how it goes. It says, write an equation. From that statement already, we know that your answer has to have equality. It has to be a literal equation, so that's got to be a feature of what you write down. I do create on partial credit, so if an element is missing here, you can still get some of the points. It's going to be an equation that expresses the fact that a function f is continuous at the number 5. So starting from this statement, when we say f is continuous, this is a reminder that there is a limit in this problem. So we have to write lim, shorthand for limit. The next element is it's relative to a specific function. So f of x has to be inside of here. So f of x gets pulled in. And then next, our limit is specific. It has to have a direction. Where are we going? How are we going there? When we say we're taking continuity, or we have continuity at a number 5, that means we're taking the limit as x tends towards 5 for the function f of x. So this would be the left-hand side. And if this was a 5-point problem, I would say lim x to 5 f of x. That's probably 3 out of 5 points already, assembling these elements. Anyone happens to know what should be on the right-hand side? It's kind of tricky, but here is the big reminder. The hint is continuity is really just direct substitution. Close. A is absolutely going to be inside there. The A value in this problem will be the 5. So 5 is over here for sure, and then just a little bit more. So something's still missing around here. Anyone spot what it should be? Yeah, good call, Kynan. It's going to be the f of 5, absolutely. So f of 5 would go here. And that's the full statement. The hint is continuity is direct substitution. And that's nice. So direct substitution just means the 5 goes inside the f of x, so you have f of 5 right here. This is what we mean by direct substitution altogether. And this is a great problem to kind of warm up to thinking about continuity, because that's going to be what the content is for Theorem 6. All of these functions, power root functions that we were analyzing on the end of Tuesday's class, exponential functions, rational functions, they're continuous on their entire domain. Some of the problems have domain issues, so we had to work a little bit harder in section 2.2 to factor things, maybe multiply by a conjugate, or maybe add fractions together. But once we did enough algebra, we ended with a continuous function, and we just literally used direct substitution to finalize the limit. So with this in mind, you're just plugging in a number for f. Let's turn over to the last limits of this section. They're some of the strangest, kind of toughest looking limits whatsoever, but these are actually the nice functions. We have a square root function already that's going to be involved, and we know root functions are continuous. Inside of it, it's a rational function. That one's also continuous. And it turns out composition of continuous functions are continuous. But let's suppose you're doing this one as an exam question and you're not too sure exactly how to start. Let's pretend it's a real exam question. And this is provided to you on that real exam one. This is on the last page. So you can flip back to this for just kind of a quick refresher on some properties. I should have opened that up before class so we don't have to watch me kind of resize things. Sorry. Let me get this resized. Place it back on the notes. So in view of this problem, which limit law is relevant aside from continuity we're about to use? You can go down here to limit law number 11. It's kind of a nice limit law, and it says if you take the nth root of a function, the limit just goes right inside that nth root. There are some things we have to be careful of. If we're taking a square root to avoid complex valued things, we'll assume that the limit is a positive value, so no complex numbers come into play. But here's that limit law. Let's throw it in just to cite it, something we're about to use. Maybe that was a little too small. Let me fix that. So this is from the exam 1 formula sheet. And it says we can do this. This is actually an intermediate step just to explain the logic of how we're using continuity. We can take the square root. So here the index n is 2. We don't have to write it in that case, but no harm if you did. Inside the limit, the square root, we take the limit as x tends towards 0 of the function x squared minus 4 divided by 2x minus 9. So with that formula, the next thing to look into is theorem 6 is a catalog of functions that are continuous, and rational functions are continuous. Because they're continuous, we just get to use direct substitution. So right here, it's a rational function. That means if you use direct substitution, it might not work. That's if you divide by 0. But plugging a 0 there gives you a -9, so 0 is in domain, and direct substitution will work. So this is rational. Use direct substitution. And here's what the direct substitution looks like. The square root is still active and alive, but 0 goes into the numerator here, so that's a 0 squared minus 4. 0 goes into the denominator, so 2 times 0 minus 9. So we're done with the limit at that spot. We've directly substituted in the value. Now it's like an order of operations problem. We can simplify this to the square root of 4/9. The negative signs cancel. So this is the root of 4 divided by the root of 9. And we get 2/3. The entire limit is done. In fact, you could have plugged in 0 right there, right at that step. This function itself, it's a composition of a square root function with a rational function, but it's also continuous. We find lots of functions are continuous. Actually, section 2.2 had the catalog of functions that were not continuous. We had to work a little harder on those. But at that stage, getting the 2/3, that problem is over. Any questions at all, folks? Analyzing theorem 6 using continuity. Notice theorem 6 is also on the handout as well. So you can use this as a guide. If you find a rational function like this, think of how we categorize these functions to know which is which when we say rational, polynomial, exponential. But when they come up, when it says it's continuous, really that's all we're using, direct substitution on each one of these. So going down the line, this one's kind of tricky, but this is an exponential function with the square root of a polynomial function on the inside. But this one's also continuous. Do we have a limit law that kind of goes with this one? Not quite with this one in this form, but composition of continuous functions are also continuous. The way you can do this one is, let me just make it a little bit bigger to start out. Start by writing that this is equal to 2 to the power of square root of, we'll plug in 0 for x squared, so 0 squared plus 1. And this one is is as well just a quick direct substitution problem. There's going to be an issue if we divide by 0 or we have a negative number inside the square root. Then we might have to do something crazy or different algebraically. But in this section emphasizing continuity, that's the whole story. Now this becomes 2 to the square root of 1, which is 2 to the power 1, but that's just 2 altogether. Then the problem just ends right at that step. That's kind of satisfying in a way, right? Continuity is tricky to think about when you're looking at the graphs, thinking about what it means, in particular, left-hand, right-hand continuity. But for these problems, just evaluating the limit to using continuity, it's nothing but a direct substitution on every single one of them. So I think I have one last one to give a try. Let's work out part C. Part C, this one is a rational function. So direct substitution also works on this. Take the value of x set going to 4, and this becomes, let's just immediately use direct substitution. We'll have x squared minus x plus 10. I'm putting a placeholder where x was, just a parenthesis. 5 times x minus 1. So 4 goes into those 3 positions where x was. Now we just have to simplify this answer. This is 16 minus 4 plus 10. Divide by 20 minus 1. That means we have a prime number 19 in the denominator, which is usually nice. It means we don't have to reduce our fraction more likely than not. And then up above, it's 12 plus 10 for a 22. So the limit of this one is 22/9, and our work is over. Well, we did it, folks. This is the rundown for the things that happen in continuity. I would say the trickiest problems, again, are the graphing ones. So that's why I thought quiz 2 should be another graphing one to give you that additional practice ahead of the exam. Quiz 2 is due on February 5th. So if you turn it in on the 5th, it's considered on time. But if you turn it in early, before Monday, I'll make every effort to get that graded so you can get the feedback on that one to help out with the exam. Haley says, how do you tell if you're supposed to factor or not? Yeah, that's the really big question with a lot of these. Let's turn to the section 2.2 to just refresh on what do we do if things go wrong? Continuity is when things go right. You just plug in a number, get a value. Section 2.2 had like 4, maybe 5 different scenarios of what all can go wrong now. So let's imagine you had just a random problem and it's, say, maybe this one right here. If you try to do a direct substitution on this one, just right as it stands, you'd plug -3 in the denominator, and standard reminder, don't forget to bring your calculator. A basic scientific calculator is what's allowed. And the testing center, they might have spares, but there's no guarantee. So it's up to you to make sure you remember your calculator. So let's try direct substitution on this. It's another rational function. You would get, sorry, not on the home row, -3 squared minus a -3 minus 12. And that's the red flag. We have 0 in the denominator. In fact, the numerator is 0 as well. You would have 9 minus 9 for 0. And 0 under 0 is indeterminate, it's undefined. So this is the red flag. You went to direct substitute, but you have a 0 in the denominator. That's when it gets more involved. That's when you have to start factoring, find things that factor and break down until you get to something simplified. So 0 in the denominator means simplify it down. But once we got there, now we used continuity right at that step. It's a different rational function, but this one is continuous at -3. So we literally just plugged in the value. We didn't say continuity here. We just said direct substitution. But they're one and the same. We just happened to study continuity more formally in terms of its limit in the very next section. But we were using it all along right in this step. Other questions so far? Yeah, absolutely. Thanks for asking about that one. And usually that's kind of one of the major questions that folks ask when it comes to limits. What should I do to even get started? How do I know I need to multiply by, say, a conjugate or otherwise? Like, say, for example, on this one here. This one was tricky, and there's one just like this on the WebAssign system as well. We know we're in trouble if we got a zero below when we directly substituted. So we had to multiply by the conjugate, expand things out till we could cancel h. And when it looks like this, our work is totally over. So those are the kinds of things that can happen on exam. Watch out for the ones that are just fully continuous on the onset, like say, this example. We really didn't have to do much but plug in the value. But watch for ones where you get zeros in the denominators and you do have to do extra algebra on. So try direct substitution first. If it fails, start to simplify. Either expand, add the fractions, factor, maybe multiply by a conjugate at the worst. I think that'd be the trickiest one. And you'll be on great shape for getting through the problem. Well, any last questions at all, folks, with continuity? Okay, well, the good news about section 3.1 is we are doing more limits. And you know, tricky problems like a limit involving this one, or even a limit involving this one, which does involve a conjugate, it does come up. So we're going to directly use all of our knowledge on taking limits right here in this section. Section 3.1 won't be on the actual exam. I better make sure to save that. But we're going to do some plenty of practice of limit material that is on the exam just in this section. So now we're turning over finally to Chapter 3, derivatives. So that's the next major concept in continuity. We're kind of running through those concepts. And derivatives are, in fact, defined in terms of a limit. But before we say what a derivative is directly, the first major concept is that of a tangent line. This is essentially where we started the entire course. We even came back to this picture to think about it. Let's start fresh with a brand new curve, a brand new tangent line, and look at this limit again to see what's going on. So I want to draw an XY plane, but emphasize quadrant one, so we can really just focus on the curve without too many distractions. So all the action is right here. It says the tangent line to the curve y equals f of x. First thing we should do is draw the y equals f of x curve. I want to make the curve do something along these lines. It comes in, kind of loops down, and then escapes again in that way. So here's y equals f of x. Looks like it's a version of x cubed, a cubic function. So we want a tangent line to that curve, y equals f of x, at some point, a f of a. That's the next thing we should track in the definition. Let's put that point down. And you know, by the way, when you read a mathematical textbook, say you turn to section 3.1 and looked at that definition, they throw the whole graph at you with every single element inside there. And sometimes it's really hard to digest that. A good way to read a math book is look at that graph they give you, but then ignore it. Look at the particular definition. See if you can draw your own, tracking through the definition and each and every little atom or element or component of it. And that's a much better way to try to read those graphs. Some of the graphs in the textbook are so busy that the information is dense and overwhelming. It's hard to really say how the definition even relates to the graph they give you. So that's what we're doing here. We're tracking through this on its element by element basis. And the next thing we have to put down is that point, a f of a. They label it as p, but I'm just going to draw here. Here's my a. Let's put it right here where it's kind of at this local maximum value. There's a point. So all the action is right in that location. And that means that's a. And going this way, this is f of a. So we want a tangent line right at that point. They tell us it's a line that goes through that point P with a slope determined this way if the limit exists. Sometimes it doesn't. So we're going to look into when the limit fails to exist in the next section, 3.2. But here's our tangent line. One way to think about a tangent line is that it's going to be the best local linear approximation to the function by a. The tangent line for this one would look like this. Let me try again. It's got to go through the point. There we go. We actually went through it. It's just a horizontal line. Let me make it look horizontal. That's kind of hard to do. Let's just imagine I drew it completely horizontal. Maybe it's off by a little bit and it wasn't exactly horizontal. You would then have the equation y equals mx plus b. So there's our equation. We're keenly interested in computing that slope. So to get the slope of the tangent line, which is done through this limit, it'll be tricky because the slope equation goes m equals y2 minus y1 divided by x2 minus x1. And also the notation's tricky. Notice there's no y1s or y2s here whatsoever, but it is a slope equation. That's because the function notation is being emphasized. So when you say y equals f of x, it also means that y1, or let's go with y2 in order, y2 is going to be f at the a plus h, and y1 is going to be the f at a. So a new really weird thing shows up here, the h. That's the next thing we should investigate. We looked into some hints on why there's an h in this problem. The idea, once again, is x2, x1 is different values for an x coordinate, but we have only one. We can't plug in a here and a here. We've divided by 0, and that's a problem for this. There's not even a limit here to try to fix it and rescue the problem. So we really do have to put in just one additional point. Let's put it out here. A plus h. Now, when we put in that second point, a plus h, we have a new point here on the graph. It's going to be at height, go horizontally to the left, f at a plus h. So now we have an x2, an x1, we have a y2 and a y1. Let's label these to track them in the formulas. x2, x1. This will be y2, and f of a will be y1. So that's the 4 moving parts inside that limit. But here's a next trouble. If we use the slope formula with those 4 different points labeled here in orange, we're getting the slope of this line. If I can draw it, this is kind of tricky. We're getting the slope of this line, and that's not what we want. We want the slope to the tangent line, the one in blue. This line is still useful, and it has a good name as well. This one's called a secant line. And we can definitely calculate the slope of the secant line, but the idea is, if this black dot gets closer and closer to the yellow dot where we want the tangency, that means h gets smaller and smaller, getting closer and closer to 0. That point moves over. We're taking a limit, and that's what this is saying to do. Take the limit as h itself, as a variable, goes to 0. So here's what the slope is going to look like on our diagram. M will be the limit as h goes to 0 of f at a plus h. That's the y2 coming from up here, minus f of a. That's the y1 coming from here. We divide the whole thing by, take the x2 next, a plus h, minus the x1, which is a. And we get a nice little cancellation here. That's kind of nice. It's a bit of a freebie. So now it's the limit as h goes to 0 of f at a plus h minus f of a, all divided by h. So that's how we calculate the slope to this tangent line. In the reading in section 3.1, there's actually 2 different 100% equivalent limits that you could write. But so we can focus on just one statement, laser focus on what it's saying. In my notes, the one I'm going to emphasize is going to be this particular limit formula when it comes up to getting the slope of the tangent line. But notice the immediate problem we hit right away. Continuity is a nice section, 2.3, but the actual limits we want to take do not have continuity. You cannot plug zero there. It's out of the domain. So all the limit laws, all the limit techniques we've been practicing, all those algebraic methods are coming back to solve this problem right here. And by the way, when we say derivatives, that's what this is, m. M is the derivative of f at a, let's say x equals a, that's a better way to say it, at x equals a. So a derivative is a slope. That's the geometric notation of it. And the thought here is this is a curve that varies almost in a linear way, but when you got closer and closer to a, it starts to level off. It becomes flat. The slope goes to zero at this point. And you know, the curve is so interesting. We would like to say, what is the slope at any point whatsoever on this graph? It's considered to be the instantaneous rate of change. So if this was, say, time and distance, this would be the value read out on your speedometer, the velocity at any moment in time. Well, that's the graph so far. And in the very next problem, we will calculate one of these limits. So we should actually be on track to calculate a couple of them and see how they go. Any questions whatsoever, folks, with the graph at the moment? Okay, let's turn to definition 2. And I think that's the same definition. Yeah, I just duplicated this here for easy reference. So with that definition there, here's our curve we're going to work on. It's a degree 3 function. It says y equals, but don't forget we have y equals f of x is always in play for all of these problems. So whether you're emphasizing the second coordinate y or you're emphasizing the function notation f of x, this is kind of just a matter of which part are you analyzing. If you're analyzing a limit formula like this one, then usually the function notation is emphasized. So if it helps out, you can just take this and just remind yourself that this is just saying the f of x in our formula is x cubed minus 5x plus 6. We want to find an equation of the tangent line to this degree 3 polynomial at that specific point, 1, 2. So if we're doing it at 1, 2, that means the value for a in our problem is 1. A is always the very first coordinate that they're giving us. So from here, a equals 1, that comes from there. And this point, 1, 2, it's on the graph of this function. So function notation would tell you that this is also saying f at 1 is 2 as well at the same exact time through that ordered pair. You could check that. If you plug in 1 here, this will be 1 minus 5 plus 6. That's 7 minus 5, so we would get a 2 indeed. We want the equation of the tangent line, which means we don't want more than just the slope. We want the whole y equals mx plus b in slope-intercept form. But the first step is just to get that slope m right there. So to get the equation, step 1 is to do this. Our slope m, the all-important derivative that we named it in the last page, is going to be the limit as h goes to 0 of f at, in place of a, we put in that first coordinate 1. F at 1 plus h minus f at 1. We already know f of 1 is 2, but in order to go just down the line in order of the formula, it's not a bad step to leave that there for the moment. Then divide by h. So that's the setup so far. And here's where, let's see, yeah, I'll go with, let's maybe change the color coding here. What's a good color? We'll stick with this one. The algebra can get intense in some of these problems. So a good way to work through this limit is kind of to divide it up. Let's do the function composition f at 1 plus h. So if this is f of x, we can re-express f of 1 plus h in this way. F at anything is that thing to the power 3 minus whatever that thing was plus 6. So this is the view I would take for that function composition. So if you plug in 1, you're plugging 1 in all those positions and getting a 2. If you plug in x, you get the original definition. But you can also plug in a 1 plus h. It will go here. In position of that x, it's 1 plus h, then to power 3. 1 plus h will go here. And let's settle this algebra. And once the dust settles, plug it back into the limit. Any questions at the moment? Just analyzing these first steps. That looks like a lot of work. So, maybe another thing you might want to do is when you see that 1 plus h power 3, let's separate out to even that problem. That's a decent amount of algebraic work all on its own. Maybe let's leave the formatting the same. I'll just do it down below. 1 plus h power 3 means you're taking 1 plus h, 1 plus h, 1 plus h. There's various tricks for doing this, but I'm just going to brute force FOIL this out, starting with the very first two. 1 plus h times 1 plus h will give us 1 plus h plus h squared. If you put in 1 plus 2h plus h squared, that'd be the great shortcut for that. But the basic FOILing of this would give us that times 1 plus h. So now we've got 1 plus 2h plus h squared times 1 plus h. We'll distribute again. I'm going to distribute from the right going into the left, the FOIL method extension. Take 1, distribute it into all 3 terms. It'll be 1 times 1 for a 1, plus 1 times 2h. So here's 2h plus 1 times h squared for h squared. The 1's kind of nice. Now take h, distribute it in through all of these. You're just taking plus h plus 2h squared plus h cubed. Really, you're just bumping up the power of h on every term. Simplify all that, and now we've got, let's see, 1 plus 2h, and h would be 3h, plus h squared, and 2h squared, h squared is 3h squared, and an h cubed. That's a lot of algebra just right there, but the idea with these kind of problems is if the algebra feels kind of extreme in a bit, just separate it out into chunks. We're doing f at 1 plus h. That's a big algebraic chunk all on its own. So with that calculated, we can return to the problem. F at 1 plus h is now equal to all this stuff. Let's substitute in what we got. 1 plus 3h plus 3h squared plus h cubed. Now back to this part. Distributed negative 5 minus 5 minus 5h plus 6. And there it all is. Let's kind of simplify this even further. I'll descend on the powers. So it'll go h cubed. Then we don't have any like terms for h squared, so plus 3h squared. As far as h goes, we have 3h minus 5h, so negative 2h. And then it goes 6 minus 5 for a 1, plus the 1 for a 2. So everything is going according to plan. We should be able to take this in blue, substitute it back over here, and we're on our way with this limit. F of 1, we know is already 2, so we're going to plug a 2 value right inside there. This is the algebra review part of it. Here, the technique algebraically was expand a bunch of stuff, hope it simplifies so we can get an answer. Any questions whatsoever, folks, getting down to there? Okay, let's bring it back to the limit. So m is now equal to a limit as h goes to 0 of h cubed plus 3h squared minus 2h plus 2. It's good to be really careful with this. Make sure you don't forget a single term, a single sign as well. So don't forget to duplicate that negative sign. Plug in 1 in here, we get a 2. And also, if the second coordinate is 2, we'll get that 2 as well. So that just plugs it in that way. And we're dividing by h. Let me fix that. we're ready to do this limit. This is about what the limits look like right at that step in section 2.2. We've seen this kind of stuff before. We have a like term we can cancel, the -2 and +2, so let's take that as well out of there. Now the slope is limit as h goes to 0 of only things involving h itself. That means you can cancel that h. We couldn't plug a 0 right away. We have a division by 0, so there was no continuity for this, even though it is a rational function in the variable h. But once we started cranking things out, combining our like terms, this h divides all three terms. I'll take the factoring view. This is what the author would most likely do right at this step. Factor h from the numerator, where the red dot is, leaving h squared plus 3h minus 2. And down below is just h. So here's a new cancellation. And this cancellation is fantastic because what we did is we have removed the discontinuity. Now the slope m is equal to the limit as h goes to 0 of nothing but h squared plus 3h minus 2. We are down to a polynomial function in the variable h. Last section told us this is continuous, and the nice fact about polynomials is their domain is all real numbers. Doesn't matter what the value is, direct substitution is a guarantee to work. 0 will be plugged here and here. So now this is the last line for the slope. We're about to get a value. The slope is h squared plus 3 times h minus 2. But we've used continuity, direct substitution, to plug in 0 for h's. And so now the slope m, let's do one more line. The slope m equals -2. So we are about there. We want the equation of the tangent line to this curve at the value m is -2. Well, we know the slope. So now we're about to get the equation. That takes us into step 2. That's a kind of a wild step 1, right? But they're all two-step processes. If you're going to get an equation of a line, you want a slope. The next thing you need is a point, but we already had the point to start. So in step 2, just pick your favorite way to build the equation of a line. I think a standard way, again, that the book would often do this would go like this. The equation would be y minus y1 equals the slope m times x minus x1. So that equation will do the job for us. We find the y1 and the x1 values just back here in the original point. That's our x1, y1. Let's just reiterate it for emphasis. x1, y1 is the original point, 1, 2. So plug in 3 different values, x1, y1, and the all-important slope of the tangent line. That's the derivative we'll call later on in these notes, -2. So this goes y minus y1 is that coordinate 2. Wrong color, 2. And wrong number, there we go, 2. The slope m by substitution is -2 that we've worked really hard to find. Then it goes x minus x1, that's that coordinate 1 right here. Now, for the sake of checking our answer, let's take this to the final steps by solving for y. WebAssign is often going to want you to solve for y anyways, but you know, this is a pretty decent equation for the line as it stands. That's the point slope format. So if you left it like that on a quiz or an exam, I'm not going to be too picky. But if you want to check your answer, it's well worth solving for y. Get it into slope intercept form. So we have y minus 2 is -2x plus 2. Add 2 to both sides, and y equals -2x plus 4. And then because we have kind of like a cloud of math looking at us, I want to emphasize that is our answer. This is the tangent line. So when it said find the equation of the tangent line, that's what we were going for, that one equation. So the limit is tricky because the algebra kind of exploded. Honestly, I would have rather have done y equals x squared, but I have a weird constraint in this one section for WebAssign. The problems that they gave me it to select from didn't have an x squared version on there, and that's really weird. So you have an x power 3 one in the homework. I felt like we should do one as well in the notes, so it didn't feel like a big jump in difficulty from class to the actual homework. Well, we're not done with this one. We should take a look into what did the tangent line even do in the first place by looking at a graph. So Desmos is going to give us a good picture of what it is we really calculated. First thing I would do in Desmos as a check on this is go f of x equals x cubed minus 5x plus 6. And this is a great tool even if you're doing homework in WebAssign. You can't bring Desmos into an exam setting, but grabbing some extra tools for concept checks while you're doing the homework and learning the topic the first time is a great idea. So here's our graph. And other thing I'd want to emphasize is the point is at 1, 2. I guess we can't see it down here. So we're really concerned about this point right here, right at 1, 2. Let me see if I can plot that. 1, 2. Okay, there it is. There's our point. That's where the tangency is supposed to happen. And now for the full check, bring in your tangent line equation. Y equals negative 2x plus 4. Now, the tangent line equation looks about right because it went through the point we plotted. But you know, there's more to tangent lines. I made a statement that we're going to put down in the notes to emphasize, but one statement I made about this purple tangent line is, it is the best, the absolute best in the world in existence, local linear approximation to that nonlinear function at the point 1, 2. So what does that mean? If this is a scientific experiment and you're really concerned about time is 1 hour, and this is maybe a population or maybe a chemical reaction that's going on here, you'd want to know the rate of the population decrease or the rate of the chemical reaction right at that point. This curve could be really complicated, but a great trick in calculus is to linearize something, simplify the problem, analyze it locally. So the way that this is the best local linear approximation is, if you zoom in on this, something kind of magic happens with this one and only tangent line. Notice the more you zoom in, the closer and closer that tangent line becomes equal to the original function. As we zoom in on this, we lose the pixel width on my display to even tell the difference. The tangent line and the function value on this range, 0.998 to 0.1002, that's a really tight range. They're just about one and the same. So it's in that sense, this is the one and only curve that best approximates the function. And also look how sensitive this is. If I got that 4 wrong and put in 0.1, it's off the chart. It just disappeared. It's gone. 0.01 is even closer, or 0.001. If I am off by 1,000, we can tell the tangent line is not approximating the original function in red whatsoever. I mean, it's pretty close, but it's not the best local linear approximation. It really has to be a dead-on exact 4. And even worse, that slope has to be exact. It could come out as any number. It could have been square root of 2. It could have been 7/3. We just happen to have an integer this time. But if you're off, even by a little on this, check out what happens. 0.001, it just moves off the line. It's not sloping in the right direction any longer. You might not be able to tell if you zoomed out on it a bit, but zoom in just a little bit more and you realize we didn't get the right slope. We're not approximating this in the right way. There's a separation between those. And again, that's just off by 1,000. If it's off by 1/10,000, that's a problem too. We don't have the best linear approximation. If we're trying to approximate a function like this, we need to work with the best tool possible. We don't want an approximation on top of an approximation. We want to put on the dead-on slope so that we have this picture. At this stage, it doesn't matter how much you zoom in, you could expire the ability of the scroll wheel to help us, or the precision of the graphing software, and this will always look like the same graph. So that's what a derivative provides us. The derivative, m equals -2, tells us the instantaneous rate of change of f of x exactly when x is 1. The instantaneous rate of change is -2 in terms of rise over run, and the tangent line itself is doing more. It's approximating the function locally in this entire range. Let's put all this into context. So the problem is over the moment we got that, -2x plus 4. I encourage you play around with this, particularly if you get the answers wrong, if you make a mistake. You can look into this and see, is there a mistake in the software WebAssign? Or do we have the wrong thing? You can just zoom in until you see it. So here's the comment we were trying to make before. This tangent line is the best local meaning you have to be around x equals 1, the first coordinate. Linear, well, that's because our tangent line is a linear equation. Approximation because the tangent line equation is not the same as the function, but it does a great approximation to y equals f of x. So that's the whole wrap up of what we were doing in chapter 2 when we were working with limits, working with continuity. Even continuity was important because we used it right at that step to finalize evaluation of this limit. Well, any questions at all, folks, with running through this one or the concepts behind it? Okay, they're pretty exciting problems. It's kind of nice that you have a very powerful and sensitive graphical check every single time you do one of these kinds of problems. The downside is the limits do get kind of heavy, so I didn't assign a lot in this section. Every problem is like 2 rolled into 1 is what it feels like. And also, another part of the good news about all of this is when it comes to doing the part of taking a derivative and getting a slope out, there are shortcuts. Major thing we're doing in the notes right here on this screen is connecting the dots of how do you define the derivative? It's a limit. So that meant we had to do chapter 2, see how to compute limits, so we know exactly what a derivative is. But in section 3.3, we're going to be looking into formulas for taking derivatives in a pretty shockingly fast way. First, let's practice a couple more. I don't think doing one is a good idea for these notes. So let's see if we can get through a part B. Same question, find the equation of the tangent line. This time it's a different curve, and this is, if we emphasize the function notation, it's f of x equals square root x plus 5. Or excuse me, 5 is what I said, but not what I wrote. Let me try again. X plus 5. To get the equation, the very first thing, like before, we want is the slope m. Now here's a good strategy for really internalizing that definition. Just write it down on paper each time you're about to use it. I mean, it's also helpful to just write it down on paper because it tells you where everything plugs in as well. It'll be the limit as h goes to 0 of f at a plus h minus f at a, all divided by h. The very first thing we want to do is determine what is the a in this problem. A volunteers to say what a should be. Is it -1 or is it +2? Absolutely, good call. It's always the very first coordinate. So -1, absolutely. So from here, we get the a value, and it is -1. And notice the shorthand. This is function notation when we say f at -1 is 2. It's conveying the same exact information at the point. But yeah, if you plug -1 inside there, you have the square root of 4, and it goes back to 2. So it gives you a couple things all at one. We have the value that goes in for f of a. We also know the a value in f at a plus h. Here's where a lot of algebra occurs sometimes. It just depends on the problem. But in this problem, f at a plus h, or hang on, let me backtrack. This should be f at 1 plus h. Let's maybe, before we proceed too far on there, let's do a substitution. I wouldn't want to do it as an a plus h just yet on this problem. Let's rewrite this as m equals limit as h goes to 0 of, plug in f at negative 1 plus h minus f at negative 1. I think it's a really good idea to do that substitution right away. And also to fix my penmanship. Let me fix that. So now we can tie in f at negative 1 is going to come from here. This will be square root. Oh, that's a mistake, isn't it? Let me try again on this one. That was positive 1 I put in. F at negative 1 plus h. Okay, it took about 3 tries, but I think we're back on the right track. Sorry about that distraction. So a good order of operations is to determine your a value, your f at that value, write down the formula, and then plug in a. So that's a great start on this one. Now with that plugged in, we go from here to here, cite the definition of the function. This is the square root of negative 1 plus h plus 5. So in place of where x was, we plug in negative 1 plus h. Those parentheses can now be dropped. So it's f at negative 1 plus h equals square root. We can make this be an h plus 4. So that just drops right down inside here. Not too much algebra this time. That's kind of nice. Sometimes it blows up. Other times it's contained. Now we have the slope m is going to be the limit. As h goes to 0, we're going to make 2 substitutions. First, this entire value is the square root of h plus 4. Now next, we knew f of negative 1 is positive 2, so we can plug that in down here. Don't forget the negative sign. And then positive 2 in this position. All divide by h. And again, if this feels like deja vu, it's because it kind of is. We didn't do this exact problem, but you've done a problem like this in WebAssign. There's one in the section 2.2 homework. We've done one like this in the lecture notes as well. So right at that step of the red dot, this on its own is a great exam 1 review problem. Let's work out this limit and see what we get on this. The big idea is, and it's a tricky problem for sure, but if we multiply it by the conjugate, that's what's going to clean up this limit. You can't use direct substitution at the moment because 0 doesn't plug in here. And that's a key feature of every single one of these problems. Direct substitution's off the table to start. But the algebraic fix is the conjugate. So there's that interesting object coming back. You take for the conjugate root h plus 4. Conjugate means flip that term, whatever sign you see, take the opposite sign. So now it's a positive 2 that goes here. Root h plus 4 plus 2. We multiply the same quantity, numerator and denominator. Now, once we get to here, we need to FOIL out through the numerator, but we leave the denominator in expanded form. And the reason for that is that h has got to go. There's a really good internal check in your algebra. We've made a mistake if we cannot cancel that h. So we leave it factored out with the expectation of forcing it to cancel. So on the next line, m is the limit as h goes to 0. And now we start FOILing. There's nice properties with square roots, though. If you take a root multiplied by the same exact root, you get the thing inside, the radicand. So h plus 4 copies in. We've eliminated the square root portion. Now this term, you really don't have to write it at all. The middle terms always cancel. But if you're doing this just from first principles, here's what it would look like. You would get 2 times, positive 2 times root h plus 4. We're done with that expansion. Now we're FOILing negative 2 times this. That's where the cancellation occurs. Now it's minus 2 times a root, h plus 4. And then from here, it's going to be -2 times +2, so -4. I'll divide by h times that big group, root h plus 4 plus 2. So we've expanded this out. The mathematical miracle is that the terms in the middle are gone. That's nice. And even more, +4 cancels with its opposite on the very far end, -4. You're left with just h. That means that cancels as well. You could do the cancellation here, but I think like we did last before in the notes, this is a lot of steps already. Let me write it one more time so the notes are just a little bit more readable. Limit as h goes to 0 of just h in the numerator, just h in the denominator, root h plus 4 plus 2. We cancel this way, leaving just 1 in the numerator. And that was our entire problem right there. Once that gone, we can now use direct substitution. In other words, this is now continuous at h is 0. We've removed the discontinuity. It's gone. You can plug 0 there, and we've got the value. Not there, sorry. You can't plug it into the number. You plug it into h, the only sole survivor. So this is 1 over root 0 plus 4 plus 2, and we have a value for that. So let me drop it down the line again. The slope m is now, that's the square root of 4, which is 2. So this is just 2 plus 2. We get exactly 1/4. Forgot to call this step 1. So there's step 1. It's kind of a nasty step 1. But the problem is effectively just about over right at that stage. Step 2 is to build the entire tangent line. But this is where the algebra kind of cools off. We'll use the point x1, y1 equals -1, 2. We already have the slope ready to go, so the equation would be y minus y1, slope m times x minus x1. Plug that whole value there. We've got our tangent line equation. Well, any last questions at all, folks, before we do these final 3 substitutions? Okay, let's put them in, solve for y, and we'll call it a day. Sorry for going right down to the minute on this one. This problem is longer than I thought. So y minus y1 is a 2, equals the slope m, which is 1/4, times x minus x1, which is a -1. So we'll be mindful to flip the negative sign on that one. Let me scroll down a little more. So it's y minus 2 is 1/4 times x plus 1/4. I call this a plus 1 and then distribute the 1/4 times it. So that's why a positive 1/4 on this. So add 2 to that, we'll get y is 1/4 x plus, it's got to be fractions. 1/4 plus 2 is really 1/4 plus 8/4, giving us 9/4 in the fraction arithmetic. And so that's our tangent line equation. We can double check this if we throw this into any kind of graphing software, but this would be the answer expected for any set of instructions that say, find a tangent line to a given curve. Find a tangent line equation, rather. Well, we did it, folks. We've got 1 minute to spare, but again, I like to leave at least a couple minutes to kind of catch our breath and ask questions. But any questions whatsoever getting through this last one? Okay, so we finally know how limits get involved. We'll return to these notes when we come back a week away from today on Thursday. So just a reminder, as far as the exam day goes, we won't have an exam, or excuse me, we won't have a lecture on next Tuesday. Sorry, I'm getting my days confused. Only because it's conceivable some people might have wanted to schedule their exam at 4:30 during class time. And also because I'm giving an exam during class time for the in-person section here in this classroom. If you have any questions about scheduling your exam, please don't hesitate to reach out. You have instructions in your Canvas inbox in Gmail, but if you don't see them, let me know and I'll resend those instructions. And if you have any questions while you're working homework, even on the weekend, please don't hesitate to write. Click the Ask My Instructor button. I'll be happy to help out. But have a great weekend, folks. Try not to work too hard, and we'll be back to the lecture notes next Thursday. Take care. Awesome, thank you. For the feedback on this, what I'll be doing is scanning it and sending you an email, so you'll know what the feedback is for it. Yep, you bet. Thanks, folks. Have a good one.